Welcome to Networks Professionals.
So, when you think of artificial intelligence, you probably picture this massive, autonomous electronic brain, right? Just crunching numbers, finding patterns, and learning entirely on its own. Honestly, it kind of feels like this impenetrable black box. But that raises a pretty massive question. Who is actually in the control room driving the machine learning process? Who really controls AI? Well, you might be surprised to learn that there is an actual control panel, and human beings are still very much in the driver's seat. Today, we're going to demystify exactly how that works. Welcome to this explainer. Today, we are literally opening up the hood of machine learning to look at the master control panel. Because despite how magical and independent AI might seem, human developers absolutely still hold the reins. Let's break down exactly how they do that. We're going to look at these complex controls and hopefully make you look at machine learning in a completely new light. Okay, let's dive into this. Here's our roadmap for today. First, we'll uncover AI's hidden control panel. Second, we'll look at the core training settings. Third, we'll explore designing the model architecture. And finally, optimizing the machine. All right, let's get into it. Section 1, AI's hidden control panel. Now, what's really interesting about this slide is the sharp contrast between what the machine actually does on its own versus what human engineers manually control. On one hand, we've got model parameters. These are things like weights and biases, basically the variables the AI learns automatically from the data during its training. But on the other hand, we have hyperparameters. These are manually tuned by developers to optimize performance. The AI doesn't just figure these out on its own. It entirely relies on humans to set them up. So, formally speaking, hyperparameters are external settings established before training even starts. Their whole purpose is to control the learning process and the model architecture itself. Think of them as the foundational rules of the game. Before the AI can go out and play and learn, a human engineer has to set up the board using these exact parameters. Moving on to Section 2, Core Training Settings. Think of these core training hyperparameters as the actual engine of our metaphorical AI machine. Just like in a high-performance sports car, these settings control the speed, the pacing, and the internal updates of the learning phase. It's all about how efficiently the machine processes its fuel, which in the case of AI is just massive, massive amounts of data. First up on that control panel is the learning rate. This dictates the step size the model takes to minimize errors. Essentially, it's pacing. Move too fast and you overshoot your target, move too slow and, well, it takes way too long. Next is batch size. That's just how many training examples the system processes before it updates its internal parameters. Then we have the number of epochs. This is the total number of times the entire dataset is passed through the model. And finally, the optimizer. This uses algorithms like ADAM or SGD, which is basically the math used to update the weights based on what the model just learned. And this brilliantly illustrates the delicate balancing act developers face, particularly with that number of epochs setting we just talked about. On one extreme, you have overfitting. This is caused by running the dataset through the model way too many times. The AI basically just memorizes the training data, but it fails completely when it sees new, real-world information. On the other extreme is underfitting, caused by too few epochs. The AI simply hasn't spent enough time learning to be useful at all. It's a constant Goldilocks problem. You have to get it just right. All right, Section 3, Designing Model Architecture. So if the training settings we just covered were the engine, architecture hyperparameters are the physical chassis. They define the structural width and depth of the AI. This is exactly where human engineers shape the actual physical complexity of the neural network that'll be doing all the heavy thinking. First, hidden layers and units specify the depth and width of the neural network. This directly impacts its ability to capture incredibly complex patterns. Then you have activation functions, which have fun little names like ReLU, sigmoid, or tan. These determine the output of a specific node, influencing the crucial nonlinearity needed for solving real-world problems. And then we have this fascinating regularization setting called the dropout rate. Let's actually focus on that dropout rate for a second because the concept is honestly pretty wild. It's the process of randomly ignoring certain neurons during training. Imagine you're trying to learn a brand new, highly complex skill, but your teacher randomly turns off different parts of your brain. Sounds like a terrible idea, right? But it's actually genius. It prevents the AI from getting too hyper-specialized to just the training data. By intentionally hobbling the network a bit, it forces the entire system to become robust and generalized, rather than just relying on a few overly smart neurons to do literally all the heavy lifting. Which brings us to Section 4, Optimizing the Machine. So, the crucial point is, we know what the levers are now. But developers don't just sit there guessing to find the perfect settings. They scale their experimentation using automated optimization techniques. You start with grid search, which is basically brute force, testing every possible predefined combination. Next is random search, which randomly samples combinations. Surprisingly, this is often faster and just as effective as checking every single box manually. And finally, we get to Bayesian optimization. This one is really clever. It uses past results to intelligently pick the next set of hyperparameters to test. In essence, developers use intelligent algorithms to figure out the best settings for their other algorithms. How cool is that? At the end of the day, AI training isn't just magic code executing in a void somewhere. As the Google Machine Learning Crash Course puts it, developers must, quote, visualize how these knobs and levers affect real-world outcomes. It absolutely requires a human being at the control panel, thoughtfully pulling these literal and metaphorical knobs and levers to shape the ultimate outcome of the intelligence. Which leaves us with one final thought to ponder. When you build your first AI, what knobs are you going to turn? Now that you've seen the master control panel and you understand things like learning rates, epochs, and dropout rates, I really hope you realize that machine learning is highly structured, very accessible, and constantly waiting for human direction. Keep exploring, keep questioning how the machine works, and we will see you.
Thanks for watching.